Okay, so let's move on to the third part, which deals with the concept of chemical kinetics. In chemical kinetics, we'll be dealing with that part of physical chemistry that will tell us how fast or how slow a reaction is actually happening. So kinetics is everything that is like that will deal with per time. So the changes in time that will be dealt in this. So what kind of changes? Chemical changes. And what chemical changes? So we'll be dealing with how the concentration of the reactants or the products change with time when a reaction is happening. Okay. So a general definition of the reaction speed. So what is basically a reaction rate? It's basically the rate with which one of the reactants disappears or one of the products appear. Okay, so let's, for example, there is a reaction, there's a simple reaction which is, say, something like this. So 2A plus 2B is giving you C. So if we are doing an experiment in which we are trying to see how, the x-axis is time, okay, and measured in time units. And here, this is the concentration of any one of these. So for the first example, let's see how the concentration of A changes. So we can expect the concentration of A to change. So if you start off with A and 2B, so at first you'll have some concentration of A, and then the concentration of E will decrease. Not necessarily in the same fashion, but in some kind of like a curve will appear when you measure. So at each time point, you keep on measuring the concentration of A in that reaction, in that system, and then you can plot a curve like this. Okay. So the reaction, the reaction rate at any small point will be basically, so for example, if at this particular time, say t, we are trying to plot we're trying to see what's the concentration of reactant A is. So after t plus dt time, we check the concentration again. Okay. So we check the concentration at t plus dt again. So in this is dt, right? The change in time, and this is the change in the concentration of A, right? And in here, we can see that since this is how it started, so as time progresses, the concentration of A is going to decrease, okay? So the rate of this particular reaction, can be written as the rate with which one of the reactants is disappearing. So what is the rate with which the concentration A is disappearing? How do you find out? So you basically take the change in the concentration of A. So I am using D to signify that the change is very small. Okay. So this is dA, and what's the time? It's dt. And I put a minus sign in here to make the rate a positive quantity. So we know inherently that dA, the quantity dA by dt, will be negative because there is a decrease in the concentration of A. So in order to make the rate as a positive quantity, I put a minus sign in here to make rate overall a positive quantity. Okay? Now, we also see that for each mole consumption of A, so if the reaction is consuming 1 mole of A, how many moles of B are getting consumed? 2 moles of B are getting consumed, right? So the consumption of B is double than that of the consumption of A, right? So if we want to get the same rate, what do you have to do? You have to divide by 2, right? You have to divide this whole thing by 2 if you are trying to measure the rate of the reaction with respect to B. Okay, why? Why did you divide this by 2? Because for each mole of A, you're consuming twice the amount of B. So since you're measuring, twice the amount of B is getting consumed, you have to divide this by a half to counteract that effect. Okay, so this is generally the rate of the reaction. So this was the reactant part, right? So this was if these two involve the reactants of the chemical kinetics. But we can also represent the rate with which the product appears, right? So what is the rate at which the product appears? So this will just become dC over dt. And I am not including any negative sign in here, because when you plot the concentration of C, you will see that since this is in the product side, the concentration of C increases with time. So this whole thing is positive in itself. So this is basically the rate of the reaction. So if you write down all of them together, so rate is basically equal to dA over dt minus, which is also equal to minus half dB, rate of change of B over dt, which is equal to the rate of change of C over dt. So for a general case, what you will have to do is you'll have to divide the rate of change of the constituents by their stoichiometric coefficient. So that's how you do it. So since the stoichiometric coefficient in here was just 1, so I did not do anything. But since the stoichiometric coefficient of B is half, we divided this whole thing by a half. Okay. All right. So this is generally how we represent the rate for any general reaction. Okay. Now there are two very important things for which we study the chemical kinetics. First is we would like to know how fast the reaction is going, right? The time with which the whole thing is, how much time does it take for a particular reaction to take place? So that is one big point. The second big thing that comes out is a reaction mechanism. So if we study chemical kinetics will be able to tell us the reaction mechanism. So the step-by-step elementary steps that a complicated reaction takes can be explained with the help of chemical kinetics. Okay, so let me write down the difference between two things. So if we want to relate the chemical kinetics with the reaction mechanisms, we have to understand the difference between an elementary reaction and a complex reaction, or this is also called an overall reaction, right? Because this is the summation of all the elementary reaction, overall reaction. So for an elementary reaction gives you the step-by-step. So let's suppose, let's think about this with a system in which there are different reactants in a system, and those reactants are reacting in the system and producing products, right? So the whole system can be explained with a general overall reaction, which will be very complicated. But what this complex overall reaction does is it sees everything in terms of stoichiometry, right? So if you have a basic reaction in which you have all the different reactants on one side and you are having the products on the other side, this will tell you the complicated overall reaction will give you a big picture and will tell you, okay, so if you start off with all these reactants, in the end you will get these many moles of these many moles of products. So this will just give you the overall big picture scenario of the whole system. This will not tell you what exactly happened in each step, because it can so happen that it can be understood like a story, right? So if something happened in your life on one particular day, right? You woke up and then you went to school and like did your classes and everything, and then at the end of the day you are telling someone about your day. So you will give them the overall big picture process, like the big picture scenario of everything that you did, right? You won't tell them exactly that you woke up at 6 and then you went to the bathroom and then you brushed your teeth and then you took a shower. You won't tell those small things, right? You will give them a big picture idea about what the particular important things that happened in your day, like in your life at that day. So this is like that. It's a complex overall big picture scenario that just tells you the start and the finish. That's it. It is not telling you about all the small things that happened when you started with this and then you reached here. So it is not telling you the intermediates, right? It is not talking about any of the intermediates, right? So this is just giving you the stoichiometric relationship between the reactants and the products, okay? It is giving you a big picture. I call this the big picture equation. In here, the elementary reaction or the mechanistic reaction gives you all those small steps that happen right from starting of the reactants until you reach the product. So this will give you every detail, like every intermediate that was produced while you started the reaction, and how did that. So this will break down this overall reaction into smaller elementary reactions. So this is called the mechanistic reaction. And the mechanistic reaction basically gives you the molecular level description of the reactions. It gives you the details of the steps. And it will tell you about all the intermediates. And this will, and if you sum all the elementary reactions, you will get the overall big picture, right? So when you sum all these, all the intermediates will be cancelled out, and you'll get just the reactants that you started with and just the product. You're not going to see any intermediates in this complicated reaction. Also, the stoichiometric coefficients in here doesn't mean much, right? So if you have a reaction, a complicated reaction in which you have, say, A and B giving you some kind of products, okay? If you just multiply with any, in here, what this means is if you start with 1 mole of A and 2 moles of B, you will get some amount of products, right? So this could be multiplied with any kind of stoichiometry, with any kind of like integral number, and you'll be fine. Like any kind of like, so you multiply, not negative numbers, but like any kind of like positive numbers, if you multiply this with, this will hold true, right? Because if I say, okay, if this is true for the overall complicated reaction, even this will be true. Okay, so even this will be true, and this is fine. I mean, yeah, I mean, you will, if you start with 10 moles of A and 20 moles of B, you will get whatever the products is. But in here, if you say A plus 2B gives you some kind of products, and you say 2A plus 2B gives you some kind of product, these two are not same, right? These two are not same. What this tells you is that this is an elementary reaction. This tells you two molecules of like each, one molecule of A and one molecule of B, they came together in one elementary step and they produced a product. In here it says 2 moles of A should come together and 2 moles of B should come together. So there should be 4 molecules in total should come together in order for that reaction to happen. Right? This is very different from this, in which only 2 molecules, like one each from A and B came together to give you a product. Right? So this is important, like the difference between these and this is huge. Okay? So you have to keep in mind the difference between an elementary reaction and a complicated overall reaction. Okay? Now in this elementary reaction, it's difficult to obtain, right? This is done experimentally. Right? You have to actually understand what are the intermediates that you are forming. So you cannot, this is easy, right? You started with something and you ended up with something. You know, like you can measure these things. But the small steps that are happening in between them, the intermediates, what are the intermediates coming in, and how they, how long do they stay? Are all the elementary reactions in the of the same rate? They might not. So what kind of reactions are actually rate limiting, right? Not all reactions will be fast. Some reactions will be slower. Some reactions will be fast. So the overall reaction will be very much dependent on each of these elementary reactions, right? Which will add up to give you this, but this is basically important to actually find out what is the nitty-gritty details, like the chemistry, the heart of the chemistry is in here. Like this is just overall big picture scenario, okay? Now, if you have any complicated reaction like this, like you have a big reaction, if I give you this, there is no way you will be able to come to this reaction, to the elementary reactions just by looking at the overall complicated complex reaction. It's not possible. Anything could have happened. So it is not possible to come to the elementary reactions theoretically from the complex reactions. You want to find out the elementary reactions, you have to do experiments to do that. You cannot move from this to this just by looking at it. It's not possible. Okay? So it is impossible to predict what constitutes the elementary, what are the constituent reactions just by looking at the overall complicated reaction. Okay? All right. So next, let's move on to finding out the rate of the reaction, right? So rate, like now let's find out how we can actually talk about the rate of the reaction. So we see this. So let's suppose you have a reaction, something like this. Okay. Now. What we saw in the elementary reaction is that, I briefly mentioned that 2 molecules have to come together, whatever that molecule number is. It might require 2 molecules to come together and collide and form a new molecule. Because say you are forming ammonia from nitrogen and hydrogen. So the nitrogen and hydrogen have to come together and collide with a minimum energy in a particular orientation, right? In order to produce that ammonia, right? It is not simply happening in all, so it's not that nitrogen and hydrogen magically become ammonia. They have to come together, collide with each other, and there is a fixed, so 3 hydrogens and 1 nitrogen atoms, when they come together, they make an ammonia. So you can understand that even Haber's process, which is N2 plus 3H2 gives 2NH3, is not going to happen in one step. There should be multiple steps, and I do not know what those intermediate steps are, right? But we know that the nitrogen and the hydrogen molecules have to come together and collide with each other with a particular frequency in a particular orientation to start these reactions. Okay, so the rate of the reaction of like the rate of the reaction which we saw was minus dA by dt. That rate is proportional to the frequency of the collisions between the A and B molecules. So it will be, the rate will be, what was the rate? So the rate was basically what we said, the rate is this, right? And this is also equal to minus dB by dt, right? And this rate is basically proportional to the collisions between A and B, which is now like should be proportional to the concentrations, right, of the A and B, or rather the activity of A and B, okay? And we saw the difference between activity and concentration in a previous video. So the frequency of the collision with which they are colliding should be dependent on the with the number of molecules that are available. The collision should be dependent on the frequency of the collisions, and that should be dependent on the activity of these individual reactants, right? So this makes sense. Now, how do you lose this proportionality sign? You bring a constant of proportion and you write something like this. Now, for all reactions that I'll be writing from now on, we will assume that this is an elementary reaction. So we do not know what's going on in a complicated reaction. So that, like I said, the complicated reaction, the overall reaction is just a simplification. It's just a big picture. So the reaction kinetics should be dealt with for elementary reaction. So if we assume this reaction is elementary, only then we can write this equation, right? Okay, now if we assume this is elementary, we can write this, and K1 is called the constant. This is a constant of proportionality, and it's called the rate constant for this reaction, okay? And rate constant is constant for a particular temperature, right? This is a function of temperature. So this will vary, and this will increase as you increase the temperature. We'll see why the rate increases as you increase the temperature. Temperature increases, collision number of the energy of the particles increases, they collide more, and therefore you increase the rate constant, basically, okay? Now, if you have another, so this was example 1, right? So if you have this reaction, how will you write the rate law, right? So this is how you write the rate. So this becomes your rate. Now, if you have, say you have a reaction like, say, A plus 2B plus C is giving you the products. Okay, then how are you going to write the rate? So then rate becomes, now we know that the rate is minus dA by dt, that's how it is defined, but how are we going to find the rate in here? We are going to find rate by using the same, because the rate of the reaction will be dependent on, will be proportional to the concentration of A, B, and C, like if this is an elementary reaction, right? So I'm just getting it K2. This is some constant, rate constant for this reaction. This will be equal to this, okay? So now we see that this is forming a general pattern, right? So this is getting raised to its stoichiometric coefficients if this is an elementary reaction. So let's generalize this. So if you have a reaction, say something like this, okay, or products, then the rate If, like again, if this is an elementary reaction, if this reaction is elementary or mechanistic, this will not be true for a complicated reaction, for a complex simplified reaction. This is only true where this represents an elementary reaction. So we know this will become some elementary, some rate constant, A raised to the power of the stoichiometric coefficient of A, B raised to the power of the stoichiometric coefficient of B, and C raised to the power of stoichiometric coefficient of C. Okay, so this is how it is. Now, as I said before, that you cannot predict the rate constant from a complicated reaction. So, for example, if you have a reaction like this, so this is H plus, this is bromate, bromide, plus 3H2O. So if this is a reaction, and I say that, okay, this reaction is basically a complicated reaction, so I cannot just apply this same rule in here and write down the rate as H plus raised to the power 6. It is not true. This has to be determined experimentally, and let's see what was the reaction, what was the rate that was calculated experimentally. So when experiments were done, we find out that this is dependent on the reactants using this function. Okay, so this is not, so Br to the power of minus, Br minus, so bromide ion to the power of 1. It is not 5, like bromate to the power of 1. Okay, this just, since this is 1 here and the stoichiometric coefficient of 1 is just a coincidence. This is not by any logic. Okay, and in here H plus is raised to the power 2. What this means is the rate, the rate of this reaction is dependent on the concentrations of bromide, bromate, and H plus. And in what fashion? In this fashion, like if you increase the concentration of bromide, if you double the concentration of bromide in here, how will the rate of, so if you double this, like if you increase the concentration of bromide, if you double that, how will the rate change? The rate will also become doubled because this is raised to the power of 1. Same for bromate. Like if you decrease the concentration of bromate here by half, the rate will be halved. In here, what is the relationship with the proton? Here we have the stoichiometric coefficient. It is raised to the power of 2. That means if the H plus concentration is increased by a factor of 2, the rate will be 4 times. Why? Because if you increase it by 2, 2 to the power of 2 becomes 4. The rate overall will change by a factor of 4. You've just increased the H plus concentration by a factor of 2, but the rate increased by a factor of 4. And how did we know that? We can only know this if we have the rate law. You cannot see this complicated reaction and just guess. Someone has to provide you with this, or you have to calculate this by doing experiments. Okay, the same, like if you decrease this by half, so the rate will become like 1/4 of what the rate was. Okay, now this could also happen that some of the reactions like might not be dependent on the reactant concentrations at all. Right? There might be certain reactions in which if you can change the concentrations of the reactants, but the rate will not depend on the concentrations of the reactants, right? So that we tell. So in here, the rate of the reaction with respect to the bromide concentration is 1, right? So it's like the rate is dependent with a factor of, like, it's directly proportional, not by any factor in here. So the order of the reaction with respect to bromide ion is 1. The order with respect to bromide ion is also 1. The order in here with respect to H plus is 2. So now we'll see how we define order and molecularity and what are the differences between these two.